Hi there once again, and welcome to another Expresso Mechanic Python tutorial. And actually this is not just a Python tutorial because there is a little bit of Expresso involved as well. And what we're about here is producing this, which I'm calling a Step Lift Effector for want of a better name. Actually, it reminds me of that famous engraving by MC Escher, the one called, I believe, Ascending and Descending. It does have a similar sort of feel to it, but of course that engraving is not really a true 3D image, it's a forced perspective image. But as I say, they're in a similar vein. But anyway, without further ado, let's see if we can make this happen. Before we get into coding in Expresso, I'm just going to show you how to make up the elements of the lift. So for this I need two cubes. I'll just command drag and create the second one, and I'll simply call this one top cube to make it distinctive. Okay, and this particular cube here is going to be the one that makes up the lift cars. Now before we go any further, I just need to resize them, so I'll make them 20 by 20 by 20. Select my lift car, and I don't want to do that. Just reset my layout to a standard layout. Thank you. That's it. Zoom in a little bit so that we can see what we're doing, and I'm going to make these, in fact I'll make both of them editable, but I'm only going to be working with this one for the moment. Make this editable, and I'm in polygon mode, which is great, and I can select these two polygons and remove them. And the next stage is to select all the remaining polygons, hit D for extrude. The offset is correct, that's set to -1, and let's apply that and see what happens. Okay, so we've gone some of the way. To finish this stage off, in here we've got create caps. If we check that box, that finishes that. So we're well on the road to making our lift car now. Moving on from here, if we select the edge tool or the edge mode and select this inner edge in here, we're in world axes, that's where we need to be. And if we select our side view, we can move this up probably to around this grid point line there. That should be fine. And then just to finish it off, what I did, I simply held down my shift key, came into my deformers and selected a bevel deformer, and then I gave it an offset of 0.2 and a subdivision value of 3, and that creates the lift car, and that looks really quite nice. It's a similar story with the top cube, so if I select that now and hit O for object, we've got our polygon mode. In our polygon mode we need to be there. I'm just going to go to my top view, and again I'll select O for object, and in my tool here I'm just going to say now only select visible elements. I'm going to check that off so we can select both the top and bottom polygons, and then we can just recheck it. And what we'll do is hit I for inner extrude, and our offset does need to be 1 centimeter, so we can apply that, and then I'll change the view to, or the display to, lines so that we can see what we're doing, and then hit MB for bridge tool, and then bridge between the two polygons here. And then if we change our display back to garage shading, we've got the basic element created there. And then to finish it off, once again I'll hold shift, come into my deformers, select bevel deformer, and set it up the same way that I did before. So 0.2 in the offset and 3 in the subdivisions. And there we have it. We've got both of our elements for our lift created. They're not too close together, but there they are. We'll leave that one there for now, it's fine. The next step is to start looking at the cloner. So we'll get a cloner in the scene and drop our cube into it. At the moment it's set up to be working as a grid array, which is wrong. We need it to be in object mode because we're going to clone onto a rectangle, and that's the next thing we need to bring in. So we'll come up to our splines and select one of those, a rectangle, set it up in the XZ plane and change its size to 101 by 101. And then reselect our cloner and drop the rectangle into the object field. And that gives us what we want. Not enough clones at the moment, so we need to change the count value to 20. And that gives us the correct amount of clones. At the moment though, they're not positioned correctly, or rather orientated correctly, so we need to work with them in order to change that. So we'll reselect our cube and then change back into model mode and select the axes. In our rotation H, we will put -90 in there, and in our rotation B, 180. And we can now see that we're in the correct formation, but there's still a problem, of course, because the corner clones need to be rotated in order to make this work properly. And that's where Python comes in. And that's what we're going to start looking at next. We'll select our cloner, grab a hold of a Python node and start work. Let's just move it down to the bottom. The first thing I'm going to do is change my layout to a coding layout, and then open the Python editor and we'll start taking a look. We want full control as opposed to parameter control, as always. We'll take away the for loop and hit execute and bring things back to the normal position there. First thing I'm going to do up here is say from C4D import utils. Two reasons for that. We are going to be creating a range mapper, as we so often do, so we will need that range map function from utils, and we also need to work with matrix rotation, which is also in there. So that's why we're importing utils. Coming down a little bit further, we've got our matrix array and obviously our count variables set up there. We also need the color array, so I'll say car is equal to, and then copy this piece of code, drop it in here and change the word matrix to color. And that's that bit sorted out. I need a frame variable, so I'll put that in now. So frame is equal to doc.getFrame .get, I beg your pardon, it should be getTime, getTime, getFrame, brackets doc.getFps, open double close. And that's our frame variable set up. And we can now bring in our current frame from the timeline. Moving on from here, we need to add some user data to our Python effector. So we'll select add user data. And our first piece of data here will be an object field, because we need to bring in a sphere that we're going to move via our lift. So we'll select a link field for that one, and that's that set up. Add another piece of user data and we'll call this spline, and not surprisingly this will be a spline that we'll use in our range mapper. For now that will do nicely. So I'll just hit OK, and in our user data we've got those two in there. We may as well create the sphere that we're going to be using, which of course later on will be a dynamic object, but we'll create that for now. It needs to be 16 centimeters in diameter, so in actual fact it's going to be 8 in the radius. So let's just put that in there. If we hit H so that we can see everything, and we'll just move in a little closer, I think, so that we can see our sphere, and then we'll move this into one of our lift cars there, and we can see that there's clearance all around it, and that's fine. What I'll also do for a second here is select the cloner and go into the transform tab and set the display to index values, and we can see that this clone here is number 0, so we're going to be working from this clone and round it in a square until we get to number 19. Great, so that's our user data set up, and we can think about moving on to the next stage of this, and that will be to set up our global variables. So back in our editor, we can say that we want global clone, global trigger, and global start time. That gets those set up. Just give myself a little bit more room. These two lines here, the has field and the full, as per usual, they're not really doing anything, but I'm just going to leave them there. Moving on from here, we can define the function. There is only one function for this because it's actually quite simple, but we're going to define that now. So we'll say def lift and start working on this. The first thing we're going to do is set up a for loop. So we'll say for I in range and just count in there because we want all of our clones to be scanned. And then we're going to set up some real values, and they're going to be the x, y, and z. So we'll say x is equal to mar I dot off dot x, y is equal to, and this is simply going to be 5, and then z is equal to mar I dot off dot z. And then to finish this off, we're going to convert these real values to a vector. So we'll say mar I dot off is equal to cinema 4D or C4D dot vector brackets x comma y multiplied by I comma z. And that completes the first little part of this, and we can actually see this in action. In order to do that, what we'll do is say if frame is equal to 0, and we'll set up our global variables. We'll define, we'll initialize those first. So we'll say clone is equal to an empty list, trigger is equal to an empty list, and start time is equal to an empty list. And then finally we can simply say lift open close, and that will call the function. I'll just change back into 3D view and we'll see what's going on, and straight away you can see it's working. So our 0 clone is now facing us, and you can see that we've set the lift up in the way that you actually saw it at the beginning of the tutorial. I'll go into the cloner here and just remove the index values. We don't just see those anymore. So you can see what I was saying about the corners here. This clone is still facing in the wrong direction. It needs to be facing in the direction of these clones here, and similarly the one over here needs to be facing in the direction of the ones going away from it there. And the same is true of the last corner here. So we need to sort these clones out next, and that's what we're going to do. So in order to do this, we'll come back into our function and we'll say if I is greater than 0 and I, and we'll use the percentage sign for a modulo 5, is equal to 0, we can then say that R is equal to C4D dot utils dot matrix rotation, or matrix rot, and it's going to be matrix rot y, and we can then say brackets C4D dot utils dot rad for radians, and we'll say minus 90 in there and do a double close. And then to finish it off, we simply say mar brackets I multiplied equals or times equals R. And let's see what we get when we run this. We just execute that. And you can see that our clones at the corners have all turned round and they're now facing in the correct directions to make this work. So that's fantastic. It's all working. So what we've done here then, just to do a little bit of a recap, we've created the real values and we've turned that vector, or created those and turned them into a vector. We've said y multiplied by I because we want every clone to be 5 units or 5 centimeters higher than the clone that precedes it. So y, we can say, is a number that's going to be multiplied. It's the number that we're going to multiply by this index value in order to achieve that stepping motion that we've got there in the clones. And then every 5th clone, or after 0, I mean we've ignored 0, so we've said that if the index value is greater than 0, so this first clone is ignored. So every 5th clone after 0, we need to turn through -90 degrees. So you can see that that works. So this clone 6 is being turned. Then we've got another 1, 2, 3, 4, and then 5 is the next clone. So once we get to 5, the modulo value will be 0, and that's the clone that we're going to turn. So you can see how that's working. And it's great. That's working fine. So the lift is effectively set up the way we need it to be in its initial state. And we can move on from here and start coding the rest of our lift function. The next thing we need to do is create a distance vector, as we've done before. So we can say pos is equal to object, and it will be get absolute position, open close. We can then say diff vect, and if you've seen any of my other tutorials, you'll have seen me do this before, equals mar brackets I dot off minus pos, and that gives us a difference vector, and then we can set the distance vector from there. So the dist vect is equal to diff vect dot get length. Now I'm not going to hold your hand this time. If you've not seen any of my other tutorials, then I'll put a card up and direct you to one where you can find out exactly what's going on here. But I've explained this a number of times in the past, and I'm not going to do that this time. So that's our distance vector set up. Moving on from here, we need to check its length. So we can say if dist vect is less than or equal to 4, if len clone is less than 1, clone dot append I. So we're getting as we've done before, we're grabbing the clone that we're currently interested in. It's the clone that the sphere is closest to. That's what we're interested in. We can also say if len trigger is less than 1, trigger dot append, and I'm going to say 1. And finally, for this stage, we can say if len start time is less than 1, start time dot append frame. We just want the current frame. Moving on from here, we can now set up our range mapper and of course our monoflop that controls the range mapper. And once again, I've done this a number of times and I've already directed you to where you can find out more information and find out the sort of the nuts and bolts of how this works. So I'm not going to go into too much detail here. So moving on from here, we can say if len trigger is equal to 1, duration is equal to frame minus start time 0. And then if duration is less than or equal to 44, we can then start working with our range mapper. So range mapper is equal to c4d.utils.range map brackets duration, comma 0, comma 44, comma, and then it will be for our output range 0 plus clone brackets 0 multiplied by 5, comma 25 plus clone 0 I'll get it right in a minute, clone 0 multiplied by 5, comma true, comma spline. What are we saying with these formula here? Let's see what we're saying. We know that this is going to be stepped, and that's really important. So the clones are not starting, I mean at the moment they're all at 0, but they're not starting from 0. They're starting from a stepped position, so all of their position wise are going to be different. So this is the way this formula works. So we're starting from 0 plus the clone's index value multiplied by 5, as we've used up here. It's the same sort of thing. We use this formula to create the actual stepping, so we've got to put it in here. So we're starting from that point there, the 0 point, which is 0 plus the clone's index value times 5, and then we're moving the clones over 25 units again from this start point, and that's why we're using a couple of little formulae in there. The true is because we're using positive values. If we were using negatives, we would have to put false in there, but we're not. We're using all positive values, so that's fine. And then the spline is the spline from the user data that we created earlier, and actually we need to drag those two user data for the object and the spline into our code here, and we're going to do that next. So what we'll do, we'll make a couple of spaces there, we'll select our Python, and we've got our user data selected from earlier. At the moment we've got nothing in the object field and we've got the spline there. So if we drag in our sphere into the object field there, and then we can pick that up and drag it into here, and then we'll change the word Python for op in the moment, but we'll just put obj because we've got object in here, we've got obj in here. So we'll say obj is equal to op, and then leave the rest of it as it is. And then the next thing we can do is drag our spline in, and we've still got to do some work with the spline, of course, because we've not set that up yet. So we can say spline is equal to op and our user data there. Good, so that's a little bit more of our Python expression set up. And what we can do now is just write the rest of this in, and then last thing we'll do, we'll set this up so that it works properly. So the next piece of code that we need to put in is going to be x is equal to, and it will be mar clone 0, and we do double close dot off dot x, y is equal to, on this occasion, our range mapper, so whatever's coming out of the range mapper is what we want there, and z is equal to mar clone 0 dot off dot z, and we can then say mar clone 0 dot off. equals C4D dot vector brackets, and it's simply X, Y and Z on this occasion. Now I'm also going to change the colour of the lift car that the sphere currently resides in, which is why I said I wanted to use the colour array. So I'm going to say car is equal to, or rather car clone 0 is equal to C4D dot vector, and we'll change it to a sort of reddish colour. We'll say 1 for red. We'll set our red at 1, and we'll set our green value to 0.2 just to make it slightly off red, and then 0 can go in the blue there. Okay, so that's that little piece of it done. And then just to finish this off, we need to say else. Now again, it depends which version of Cinema 4D you're using, but you can either say del clone and put a colon between two brackets, or if you've got if you're using R24 as I am, or S24 I should say, as I am, what I can say is simply clone dot clear and then open close, and that works perfectly well. Okay, so I'll do the same for trigger. So I'll say trigger dot clear and start time dot clear, and that completes the code. That's as much code as we need to do to make this work. Okay, so our next port of call then will be to set up this spline and take things from there. And then after we've done that, we need to move on and do a little bit of Expresso, and of course set up the dynamics. Right, let's have a go at this spline. I'll just twirl this open. My first point, I'm going to put a 0 on the Y, and I'm going to set it to 0.2. It doesn't have to be exact, but I'll set it at 0.2 in the X. Second point I'm going to place at 0.4 on the X and at 1 on the Y. And then my third point I'll set at 0.8 on the X and 1 on the Y. And finally 0 on the Y and 1 on the X for the final point. The tangents, let's set those to 125 or minus 125 in this particular case, but let's set them all the same. That's fine, that one's already there, and this one just wants to be 125, and that should work fine. That spline will do the job for us, and that's all you need to do in there. And you can see how this is going to work. So we're going to have a pause, then we're going to raise up, another pause, and then return to our start position. So that's how our clones are going to be moved. Before I move on to the dynamics, I'm just going to select Python in here. I'm just going to clear that out and then execute this code, see if there's any problems. Okay, we've got a syntax error, and it is in line 59, which is here. Okay, rang mapper, I see. Let's make that range mapper, that's correct. That's all right. Let's see if we get any more problems. No, everything seems to be working now. It's all jumped back into its correct position. Okay, so that's all looking good. Before we actually move on to the dynamics, there's still a couple of finishing touches that we need to put to the code in order to get it to work exactly as we want it to. The first thing we need to say is else, down here, lift. So we need to set everything up at frame 0, and at all other times we need to be calling the lift function. So we've set that up. The next thing to do is copy this line of code, place it down here, and simply say color, comma, car, to update the color array as well as the matrix array. And that should be as much as we need to do in the code. Great. So from here we can move on and we can think about setting up our dynamics. We also need to put in, while we think about it, our top element here, because that's completely separate from the rest of the lift cars there. In fact, it's a static object that doesn't actually move, and it helps, well, it's there so that we return the sphere back to the start. So if we go into our top view and say H, and we get a hold of our top cube, and we'll just bring it down somewhere here. I'm going to do this more or less by eye. If we've got 52 in there, it should be it's about 50 point something, but we'll use 50 as a start. And the same with here, we'll just put 50 in there to get it to that corner. I know its height will be 100. That much is absolutely true. Let's go into True 3D mode and have a quick look and see what we can see. I mean, it looks pretty good the way it's set up. Let's just take a look in the orthogonal view here. And just see what you can see here, though, that it's not quite in the right position. It needs to be pulled sort of over here. So there needs to be a little bit of a gap between itself and the clone that precedes it. But that should be fine now. I don't think there'll be a major problem with that. If there are, we can do some tweaks on it, but it should be okay where it is. And you can see we've got our first clone turning red. So we can see that our code is actually doing something. That's great. Next thing for us then is definitely to set up the dynamics. So we've got our top cube selected and we may as well give that its dynamic tag. So we'll come down to Simulations Collider Body here. We don't need to inherit the tag, so we can say none and we can turn that off in the individual elements there. We can set those up like that. It's set up as a static mesh. That's absolutely fine. And we can leave everything else the same. It's perfectly good. So that's our top cube set up. I'm going to put the dynamics tag on the cube rather than the cloner. So I'm going to select my cube and come down to simulation again, collider body for our lift car. Again, apply to children. Well, there aren't really any, although I suppose it does have a bevel. We'll leave that as it is. We'll leave that set up as it is. I think that'll be okay. And we'll call this one, for now, a moving mesh. We'll see if it works, or we could say a convex hull. We'll say, in fact, I'll tell you what, we will say convex hull. Let's set it up as a convex hull. And finally, our sphere, if we say rigging tags, oh no, not rigging, simulation tags, rigid body. Again, we can say none in the inherit tag and off in the individual elements because there definitely are no children. And the shape, again, we'll make it into a convex hull. That should be fine. Okay, let's just give this a run and see if we've got any problems. Interesting. Okay, so something it doesn't like there. So we've got convex hull there. Let's just go into our cube here. And let's see if we set this up as a moving mesh and see if that makes any difference. Ah, that's better, isn't it? Well, it sort of worked, didn't it? It tried to, and then we got a bit of a problem. So what have we got actually giving us a problem here? We may have something in the code, it looks like. Let's have a go. Let's just do this again. Yeah, okay. So it's saying local variable range mapper is referenced before assignment. That's probably going to be a structural thing. Let's have a look. What have we got here? Yeah, I think, yeah, I see what the problem is. I've got if duration is less than or equal to 44, and I've got all of this in here. Yeah, so what I've got to do, I've actually, it's the tab that's wrong. So I've got to tab those into there. I also need to tab these over there. So it's a little bit of a structural error that I created there. I think that should be okay now. Let's have a go. No, still not. What's the problem? Local variable range mapper reference before assignment. Let's have a look. Range mapper. That's very strange. Well, y is equal to range mapper. That's there. It should be correct. Should be correct. Yeah, I don't see any reason why that isn't correct. That's very strange. I don't quite understand that one at all. Y is equal to range mapper, X, Y, Z. That's fascinating. I'm not quite sure why that's doing that. Very, very interesting. Well, the only thing I can think of to try, this is a long shot, but I'll give it a go. I'm going to take this code out of here and I'm going to say, let's do it again. So clone.clear trigger.clear and start time.clear. You never know, it might be the thing that makes the difference. But let's give it a go. Right, we're back to normal there, that's fine. Let's just fire this up. You've got to be kidding me. Let's just give ourselves some more frames here. Honestly, it is. That's the thing that's made it work. Well, that has got to be the most bizarre thing I've ever seen in any of the tutorials that I've done. I mean, when I did that, I thought, well, I'm just clutching at straws here. But I don't know. I can't even begin to understand how this is possible. And I really don't have an explanation for this. It's just one of those really weird ghosts in the machine things that just sometimes happen with computers. That is extraordinary. I mean, I knew when I looked at this code, I thought, well, at first I had the tabulation wrong. That's fine. But the range mapper is assigned here, and yet 2 lines away from it, we're referencing the range mapper before it's been assigned. That's what we were getting told. But I knew that that was clearly absurd. But I would never have believed doing what I've just done there could be the thing that would sort it out. That really is the strangest thing I've ever seen. But it's worked. It's worked. In a way, it's perhaps a good thing that you've seen that, because you now know what to do if you ever come across a situation similar to this one. Just take out some code and type it in again and see if it makes a difference. But, you know, there you go. Such is life. Right, let's create the Expresso expression before it has another brainstorm and changes its mind. We'll get a null and we'll call that Expresso. And then go to our tags and come down to programming tags and select Expresso. And we've got our window open. First thing I need to drag in is my sphere. And I'm going to give it a couple of outputs, and they're going to be coordinates position Y, and position Z. The next thing I need are 3 compares. So I'll command drag to copy another couple of those. The first 2 compares, I'm going to plumb the output or the position Y from the sphere into the top inputs, and the position Z I'm going to plumb into the input 1 of the bottom compare. Let's set these up with functions. I'm going to explain a bit later what this is doing. I mean, basically what it's doing, we're going to change the color of the top cube here when the sphere drops through it. That's what this expression is going to be doing, but we'll look at the detail a little bit later. So the function of this top compare is going to be less than or equal to, and the input 2 will be 100. The second compare, I'm going to say greater than or equal to, and in here I'm going to put 75 as a starting point. So we may do a little bit of a tweak on that later, but we'll use it as a starting point. The bottom compare, I'm going to say greater than or equal to 50. Moving on from here, I need 2 bools. These are both going to be ands in the function, so we don't need to change anything. So I'll just command drag to copy a second one. The outputs from the top compare will go into the input 1 of the first bool, and similarly the compares output for the second compares output will go in the input 2 of the first bool, and then the output of this bool will be plumbed into the input of the second bool, and the output of the compare at the bottom goes into the second input of the last bool there. Moving on from here, we need a condition node, and this will be set to a data type of color. And we'll set the swatches up. So in the input 2, we'll say we want 178 in the red, 202 in the green, and 233 in the blue, and that gives us a nice sort of greyish sort of blue. And in the second swatch we want a 16 in the red, in the green 81, and 179 in the blue, and that gives us a darker blue. We can then plumb the output of the bool into the switch, and then the final step is to bring in the top cube, and in its input we can say we want, in the basic properties, colour, and we can plumb the output of the condition into the input. And that completes that part of the expression. So let's see if we get anything working. Actually, at the moment we won't, because there's one more step that we need to do. We need to select our top cube, and in the basic tab here the display color needs to be set to either on or automatic. I just use automatic, and you'll see straight away that we've got a slate blue color on the top cube there, so we know that it is actually doing the job. Right, so let's run the sequence and we'll see what happens here. What I'll do, I'll let this run and I'll put a cross dissolve in and come back to you by the power of editing. Yep, and it works fine. Great, that's working perfectly well. Now, I did say that we could actually have a look at this compare here. I put 75 in there, and I said that we could probably, use it as a starting point. Well, we'll see what happens when we put it at 65. And then we'll go back to the beginning of our animation and play again. Let's see if it does anything that we don't like. Ah, yeah, it does. There was a slight glitch, wasn't there? The top cube momentarily changed to darker blue. So you've got to be careful. I mean, I've shown you that. I knew it was going to happen, actually. The reason I've shown you that is because you've got to be a little bit wary of what you put in this second compare. So I found that 75 actually works probably best, so I'm going to leave it at that, but it was worth just showing you that so that you could see what was going to happen. But yeah, that's the Expresso. So basically, but when the cube, or when the sphere I should say, has reached the top cube, when it's between 100 and 65 centimeters in height, and also when it's either greater than or equal to 50 along its z-axis, that's the point at which you can change the color of the top cube from a slate blue to a darker blue. Between those values, when those conditions are satisfied, that's the only time that it can change, and that's exactly what we're doing here. So that's why we've got the double and in there, and then the switch to the condition, and then that's all there is to it. So it's a simple expression, just to change the color of the top cube at the correct time. That's all we're doing with that. Okay, and that just about completes that part of it. Now currently the lift is actually fixed at a certain height, but it would be nice if we could make it adjustable. And as a bonus, I'm going to show you how to do that right now. So what we need to do first is come back into our Python here, and or our Python effector, and we're going to add some more user data. So the first thing we're going to do is add what I'm going to be calling the lift height. So we'll do this first, and this is going to be, it will be a float, but it will also be in the interface. We'll change it to a float slider. It'll be a real value, and we'll do it in steps of 1, and our minimum step we'll put as 3, and or our minimum height I should say, as we'll put as 3, and 12 as our maximum height, and the default value we'll leave at 3, and we don't really need to change anything else. So that's the first piece of user data added. Second piece of data is going to be our what I'm going to call our top cube height multiplier. Bit of a mouthful, but it does make sense. And again, I'm going to leave that as a float, and it's going to be a real value. And apart from that, I don't need to change anything else. It's perfectly good. So we can just hit OK, and those two have been added for us. Moving on from here, we need to add a few lines to our code, and we'll need to pull in our lift height for a start. That needs to be pulled in, and we need to place that here. So rather than saying that y is equal to 5, we need to say that y is equal to op user data 3. That will be fine. So our lift height's being dragged into there. Moving on from here, we need to drag in our cube height multiplier, or our top cube height multiplier, and that needs to be placed just in here. And we need to say op, just get it in the correct place, and we'll put a bit of space between it and the code that precedes it and follows it, and we'll say is equal to y. So this is actually, and this is input data technically here. This is going to be output data, because this is going to be passed to an Expresso expression, or to our expression. We're going to do some more work in there. And that's where we need to go next. So let's open our expression again and start doing a bit more work in here. We need a bigger window, and I'm going to drag everything over to this side so I've got a bit more room. The first thing I need to do is drag the Python effector into here, and then come down to user data at the bottom and say top cube height multiplier. Get that into there, and then I need a couple of math nodes. The first one, well, in fact, I'll grab one of those in and just command drag to copy it. The first one is going to be, oops, I don't want to do that. The first one's going to be a multiply, and the second one will be a subtract. In the multiply, I'm going to plumb the output of the Python there into the first input, and I'm going to multiply by 20, and the output I'm going to plumb into the top input of the subtract, and I'm going to subtract 30 from the result. So we're technically multiplying the multiplier by the height of our cubes, and we're subtracting 30. This is to prevent any glitching with the color again. That's what I'm doing that for. So I'm subtracting 30 in order to do that, so that when the height of the lift is actually at its lowest point, subtracting that 30 there will prevent any glitching with the color as we did before. That's why that's being done. And then the output of this subtract, I can plumb into the bottom input of this compare. So as long as we're greater than or equal to the output, or our position y from our sphere is greater than or equal to the output of this subtract, we're going to get a positive result at the output here from now on. So we've just enhanced that a little bit further. The next thing I'm going to do is actually drag out or copy another compare here, and in our sphere I'm also going to add the position x. Drag it up to the top of there if I can. So I've got the x, y and z in the sphere now, and I'm going to plumb that into the compare at the top, and this is going to be greater than or equal to 50, as with the z. Oh, I've done it again. Just get that to 100%, and that is going to help us to tighten things up even further and make sure that we don't get any more glitches creeping in. And we're also going to add another bool, plumb this one into the top input there, the input number 1, and plumb the output of the second bool, what has now become the second bool, into the input 2 of our third bool. And then from here we simply need to use the output of this bool to control the switch of the top cube. The last step, I'm just going to bring the top cube down here, and I'm going to add coordinates, position, position Y in here, and I'm going to plumb the output of our math multiply into this input, and that's going to control the height of our top cube, because obviously it's a separate item from all of the other lift cars. They're clones, it's a separate entity. Right, so let's just see if we've got anything working here, and I'm pretty sure that we do have a little error of some kind creeping in. I'm not quite sure why that might be. Yeah, it's not quite working yet, so we need to do a little bit of debugging. In actual fact, I think if I just click on the Python here, yeah, that's moved. Yeah, what was happening is there was nothing in here. It just needed a quick update, and then do it again, and then we've got everything back to where we need to be. So there is no problem. If I select the Python and I move the height multiplier, or the lift height, I should say, straight away it works, because of course the height multiplier is past the value of the lift height, which is what's happening here. So we can see that Y is the input value, so the lift height is the input value, and straight away the output value is here, and that's equal to Y. So the two are synchronized, and then in the expression the top cube height multiplier is passed to the math multiply, which is then subsequently passed to the position Y of the cube, which then places the cube at the correct height position. And then the remaining parts of the expression are simply used to control the status of the condition node. To switch the colour of the top cube to darker blue at the correct time. That's all that's going to happen. So that's working fine. So if we go into the Python, you'll see that if you get a hold of this and move it, there is a lag, and you can't do much about that, unfortunately. It's just the way that the Expresso and Python work together. They're okay as long as you sort of click on the little arrows here, but if you drag, you'll find that there will be lag in there. There's just nothing you can do about it, unfortunately. But that's got everything going there. However, there is one more thing that we need to do in order to make this work properly now. We can no longer say 0 plus clone times 5. It's got to be times Y, because of course that's now a variable height as opposed to a fixed height. So we've got to say times Y there. And this 25 here plus clone times 5, obviously it's going to be times Y again. We can put that in for a start. But we've also now got to say Y plus 20 plus clone 0 times Y. That's the formula now to make this work. Okay, so that's important. We'll just do that there just to make it a little bit easier to see what it is. So Y plus 20 plus clone 0 times Y, and that will make this work. If we run that now, we can just double check to see that we're okay with it. It should be fine, and it is. And if we just move the height, it's obviously thrown the sphere off, but that's not a problem. If we run it again, you can see that the heights of the clones are now behaving as they should. It's all working perfectly well. So that's fine. That's the first little thing that we can do, and that was the thing that we had to do. The thing that we might like to try though is to do something with the color array here. Rather than just leave it as red all the time, what we can do is actually make them change from red to blue over the entire sequence. So we'll do that by saying here, we'll say 1 minus 0.007 multiplied by Y. So again, we're using the height to actually change the color of the clones as they raise up and down, and that will give us something interesting. We'll put 0 this time in the green, and here we'll say plus 0.007 multiplied by Y in the blue. And let's see what happens. They do change colour subtly as they raise and lower, but also their starting colours are changing. They're gradually changing from red to blue. It just makes it, I think, a little bit more interesting. So it's just an idea. You don't have to do it. It's just a sort of art direction thing. I just quite like the idea of it. And yeah, and then they're more purple now when they start, aren't they? They'll just about be blue by the time they reach the end. And we've got things working there. However, there is one thing I saw that I didn't like. That seemed very glitchy, this top cubicle end, didn't it? And I don't like that glitchiness. So let's see if we can do something about it. The only thing I can suggest we do is remove this and put this back as it was. So let's try ignoring this and see if it makes a difference. Let's just run that again. I'll tell you, I'll take it back to 0 and we'll run it from there. Let's just see what we get. There's a little bit of glitchiness in it as well, so we probably need to do some work. Have a look, see what we get. That's pretty much why I put the X in there, but I want to just see what happens here. Let's have a look, see if we get any glitchiness in it. Well, that's better. That top cube is better there. But let's just see. Yeah, we're getting a little bit of glitchiness in there. Let's just see if we can, just working with that multiplying and the subtracting there. Let's have a look, see what we've got here. So in our subtract, so this is the bit that's going to make it different. Let's just see what we can do here. If we try a different number in that subtract, let's try 40 in there and just see what happens. See if that makes any real difference to it. No, it's worse. So instead of subtracting 40, let's try 20 instead of 30. Just see what happens. So far, so good. Yeah. This may fix the problem. And if it does, I'll leave it like that and I won't change it anymore. But it just, I don't like to see sort of glitching in there. It's much better if it's the way we just saw it. Let's have a look, see what we get this time. Yeah, that's much better. I much prefer that. I think that's better. Yeah, still a little bit of a glitch there though. And it could be, I mean, the sphere is very bouncy. Now, you can play around with the dynamics and try and change that, or possibly make this duration slightly longer and take some of the bounciness out of there. It's just a question really, I think, of art directing this again the way you prefer to see it. But there are definitely things you can do to stop that sphere from being as bouncy as it is. This is just one. As I say, if you like to play around with the dynamics, you may even be able to make the mass of the sphere slightly different so that it's a heavier object, and that can help to make it less bouncy. But yeah, I mean, this is working okay. But yeah, as I say, entirely up to you what you do. Have a play around with the dynamics. You can do what I've just done here and change the timing. You know, just see what sort of suits your mood. But yeah, I mean, I'm happy with that now. I think that's much better. Anyway, that just about wraps this one up. So that's how you go about creating a step lift effector using Python and a little bit of Expresso. And if you've enjoyed the video, then please give it a thumbs up. And if you haven't already, please subscribe to the channel. And of course, share the video with your friends on Instagram or wherever you happen to be on social media, because all of this good stuff helps the channel keep going in the right direction. But anyway, for now, that just about brings this one to a finish. So I'll see you very soon on the next tutorial.